Hi, this is part 2 of our series on matrices, in particular the kind of questions they could ask you on the ACT math exam. So, there's 3 things not covered last time that may show up on the ACT math exam. These are more obscure, but if you want to make a 30 or higher on the ACT math exam, it doesn't hurt to know this stuff because it could show up. First, let's go over how to find the determinant of a 2 by 2 matrix. A 2 by 2 matrix looks something like this: A, B, C, and D. That's a 2 by 2 matrix. It's got 2 rows, A, B, C, D, 2 columns, A, C, B, D. 2 by 2. Okay? Determinant, sometimes abbreviated DET for determinant. Determinant. You just simply multiply A times D and subtract C times B. So the determinant is A times D minus C times B. A times D minus B, C times B, or B times C. Let's look at a real example. Let's say we need to find the determinant of 5, 3, 4, 5. Something like that. Well, that's going to be 5 times 5, which is 25, minus 4 times 3, which is 12. 25 minus 12 is 13. That's the determinant. Okay? What is the determinant? Why do you need to know this? Well, you need to know it because it could show up on the exam. That's one thing. But what it really is, if you want to think about it, is a rough size of what the matrix represents. If you're dealing with vectors and you're having a matrix, a 2 by 2 matrix represent a vector, then it's roughly the size of the parallelogram formed by the vectors when graphed in the xy plane. Actually, it's not roughly that, it's actually that, but don't worry about that. Just know it's roughly the size. In fact, an abbreviation for determinant for a matrix is not just det, but also the absolute value. So A, B, C, D. If you ever see absolute value signs around a matrix, that means what's the determinant of it. What's the one single digit number value that could represent that matrix? How big is it? So they may give you a question on the exam that doesn't have you actually computing the determinant, but where you need to know that it kind of represents the size of the matrix. How big is the thing? So for example, they could just ask you, which of these aspects of a matrix represents the total size? And it can give you things like the eigenvalue, the determinant, and some other crap. And you just say, it's the determinant. The determinant's the size, roughly. It's how big it is. So just think of it that way. No, determinant means rough size, and there you go. One quick note, unlike the absolute value, this could be negative. You can have a negative size. Like think of something instead of the first quadrant, could be the fourth quadrant for size. When you're plotting it, that's considered negative because it's got a negative y component. That's okay, but it's still a single number. It says, oh wait, this is negative down here. But anyway, just know it's down to a single number and it roughly represents size. Let's go through some more examples of finding determinants. This one's for you. Go ahead and find the determinant of 5322. Pause the video, resume when you're ready. All right, ready? Well, this is simply going to be 5 times 2 minus 2 times 3, which is 10 minus 6, which is 4. Okay, let's try another one. Here you go. Find the determinant of the matrix minus 2 minus 6 minus 5 minus 3. Ready? All right. That's equal to minus 2 times minus 3 minus 5 times minus 6. Probably should have put these all in parentheses. So that's going to be 6 minus 30, which equals minus 24. Got it? Good. Let's do one more, shall we? All right, for this one, the matrix is 5, 8, 3, 7. Go ahead. Remember, the absolute values are shorthand for determinant. So this is just the determinant of this matrix. So this is going to equal 5 times 7 minus 3 times 8, which equals 35 minus 24, which equals 11. Can you find the determinant of larger matrices? Yes! It's just a lot harder. They're not going to expect you to do that on this test. I have not seen any old ACT practice exams where they ask you to find the determinant of anything but a 2 by 2 matrix. That said, they have asked a question like this before, so give it a shot. The determinant of this matrix 3x, 1, 2 is x squared. If x is greater than 0, what is x? Give some time, pause the video, Resume when you're done. All right, they're telling you the determinant of this thing is x squared, meaning the determinant equals x squared. Well, what is the determinant? The determinant is 6 minus x equals x squared. See where we're going with this now? That means x squared plus x minus 6 equals 0. Just adding x to both sides, subtracting 6 from both sides, and you have it equals 0. This can be factored into x. Let's see, two things that multiply to give minus 6, add to give 1. That'd be 3 and minus 2. There we go. So x will be minus 3 or 2, but they're saying x is positive, so x equals 2. They could definitely throw a word problem in there like that with the determinant, where you have to find the determinant, but then you got to do a little bit more with that. And they love quadratics, so they could very easily, and they have asked questions like this before, where they give you a fairly easy determinant, but geez, they got a variable in there. Oh no, still the same formula. Just multiply these, subtract the multiplication of those. That's going to be 3 times 2, which is 6, minus 1 times x, which is just x. And then set that equal to that, because that's what they're telling you. If the determinant is x squared, then it's a simple quadratic. Factor, you're done. Or if you couldn't factor, you could use the quadratic equation. That's fine too, but it's a time-sensitive test. Factor first if you can. Maybe we'll have a whole other video on quadratics later. We'll see. All right, let's move on to the second topic that you should know when it comes to more advanced matrix stuff, is matrix multiplication. Now, one thing about matrix multiplication, not just scalar multiplication, we covered that last time, but actually multiplying two matrices together, is you can only do it if the first matrix has the same number of columns as the second matrix has rows. Okay? In other words, if you have something like this, let's say 3, 2, 5, 1 times 2, 1. Can you multiply those two matrices? This is a 2 by 2 matrix. It's 2 rows, 1 row, 2 row, and 2 columns. 1 row, 2 columns. 2 rows, 2 columns. This is a 2 by 1 matrix. 2 rows, but only 1 column. Yes, you can. These two numbers, an easy way to think about it, those two that are next to each other with the dimensions, this is a 2 by 2, that's a 2 by 1. Those two inside numbers, this representing the columns, this representing the rows of the next one, columns of the first one, rows of the second one, they have to be the same number. The resulting matrix would be a 2 by 1 matrix. It would look like that in this case. The outside numbers, 2 and 1. Know that a matrix, when you're multiplying two matrices, it can only happen if the inside numbers here, when you write down the dimensions, dimension being row by column count, these two numbers have to be the same, the two inside ones. The number of columns in the first matrix, the number of rows in the second matrix. They have to be the same, otherwise you can't multiply. And then the end result will be this times this, the outer numbers, 2 by 1, okay? Quick thing on how to multiply. I'm going to leave a couple links for that. I'll just do this one really quickly because it's a pretty easy one. But it's really just, you start with the rows here and you go by columns here. Rows, columns, rows, columns. You do all the rows here by all the columns. The next row, all the columns. Next row, all the columns. You end up filling in all the values here. In this case, it's 3 times 2, which is 6, plus 2 times 1, which is 2. This is 5 times 2, which is 10. Plus 1 times 1, which is that, which is 1, this means this is 8 and 11. That's it. There's definitely more complicated ones when you get in 2 by 2s, 3 by 3s, but I'm blowing over the actual multiplication because you don't really need it. I have not seen a single question yet where it's needed. It's nice to have in some problems, but it's not needed. One particular problem I've seen recently was one where they're dealing with a zoo. Maybe I can flip it up on the screen here, where they're talking about the amount of water that the animals in the zoo drinks. I forget, it's like lions and giraffes and bears, and there's, this number of each of the animals, or they drink this much water, and how much water total do they drink, which multiplication of matrices, where they have one matrix that represents the animals, the other represents the water, or something like that, which multiplication represents the total amount of water being drank. Well, here's the thing. If you want the total amount of water, you want a number, right? Like the number of gallons. You want a number. Okay? In that case, you want a 1 by 1 matrix when you're done. So it's just one number. So they'll give you a bunch of answers, A, B, C, and D. You'll probably see right off the bat, 3 of those wouldn't work at all or impossible, because if you look at the dimensions, row, column, this number of columns, this number of rows don't match. So you'd eliminate a bunch of answers right there. And then of the ones that are left, you'd have, say, a 1 by 3 matrix times a 3 by 1. And then you also have a 2 by 1 multiplied by 1 by 2, something like that. Well, the end result of this one, yes, you can multiply this because these 3's are the same. You can multiply this, these 1's are the same, but this is going to end in a 1 by 1 matrix. This is going to end in a 2 by 2 matrix. If you want a single number, you want a 1 by 1 matrix. That's just one number. One row, one column, one number. 2 by 2, you're going to end up with a matrix that looks like this. That doesn't give you a single number. No bueno on that one. So what I'm saying is it's just helpful to know about the dimensions, okay? So let's run through a few examples, shall we? All right, let's look at some matrix multiplication examples here. Can you do this? And if so, what's the resulting matrix dimension? Give it a shot. This is 2, 1, 5, 3, and 1, 2 right here. All right, this is a 2 by 2 matrix. 2 rows, 2 columns. This is 2 rows and 1 column. Yes, you can do it because those two numbers are the same. What do you end up with? You end up with a 2 by 1 matrix. You'll end up with something that looks like this, a 2 rows, 2 rows, but only 1 column. Okay? How about this one? Can you do this? This guy right here. This is a matrix. This is another matrix. Can you multiply those? What do you think? Yes, you can. This is a 2 by 2 and this is a 2 by 2. This is one of the most easy cases. This is a 2 by 2 as well. Yes, you can do it. They're all 2's. You're going to end up with a 2 by 2. All good. How about this guy? This is 1, 2, and this is 7, 8. Can you multiply those together? And if so, what's the resulting dimension? Well, this is 1 row by 2 columns, and this is 2 rows by 1 column. Yes, you can. The inside numbers here, 2 and 2, those equal each other. This is the same number of columns as this is rows. And what will you end up with? You'll end up with a 1 by 1. In other words, just a single number. A single number, by the way, will be 1 times 7 plus 2 times 8, which is 7 plus 16, which is, what is 7 plus 16? 23? I think it's 23. Let's say it's 23. All right. Can you do this one? Yeah, it's very similar to this one over here. This is 1 row, 2 columns, 1 by 2, and this is 2 rows, 1 column. Same thing, it'll be a 1-dimensional matrix. It'll be just one number, a 1 by 1 matrix, which basically is a number. So in this case, it's again 7 plus 16. I just did almost the same thing here, just reversed the numbers around a little bit. So this is also, whatever 7 plus 16 is, which is 23. It's just in matrix form, but still just the number 23. How about this guy? Can you multiply those two together? 7, 8, then 2, 2, 3, 4. What do you think? This is a 1 by 2. This is a 2 by 2. Yes, you can. 2 is the same thing as 2. You can multiply those. What do you end up with? You end up with a 1 by 2. In fact, let's do it real quick. This is 7 times 2, which is 14, plus 8 times 3, which is 24. 14 plus 24, what is that, 38? Then you have 7 times 2, same thing, 14. 8 times 4, 32. What is 14 plus, I'm sorry, not a plus sign there. What is 14 plus 32? 14 plus 30, what is that, 46? Or something like that. That's that. That's how that would work. But again, you don't need to know how to do the actual multiplication. If you want to learn it, I'll provide some links in the description below, but that's that. Let's go to some ones that may work out, may not work out. You tell me if you can multiply these or not. Because I've noticed on some of the questions they give, on some practice ACT exams, they will literally give you something where you have to choose between a bunch of different matrix multiplications, and some of them are just impossible. So if you can rule out the impossible examples right off the bat, boom. That makes it a lot easier, huh? All right, let's look at these. You tell me if they're possible or not, and if they are possible, what's the resulting dimension? If they're not possible, tell me why. How about this one right here? It's 1, 2, 1, 2, 3. You can pause the video if needed, just FYI. All right. So, well, this is a, let's see, how many rows? 1 row. How many columns? 2. And this is a 3 row by 1 column. No, impossible, because these two numbers do not match. This does not have the same number of columns as this has rows. Impossible. Can't do it. How about this guy? Right here. All right, resumed, you're paused, resumed. Okay, here we go. Well, how many rows? This has 3 rows and 1 column, and this has 1 row and 3 columns. Yes, you can do these. These two numbers are the same. This has the same number of columns as this has rows. And what would the result be? It'd be a 3 by 3 matrix. How about this guy? Is that possible? This is 1, 2, 3, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, let's see. This is a 3 by 1, 3 rows, 1 column, and this is a 3 by 3. No, you cannot do that. This 1 does not equal that 3. This does not have the same number of columns as this has rows. So, no bueno. How about this guy? This is 1, 2, 3, 4, and 1, 2. Is it possible? Well, let's see. This is a 2 by 2, and this is a 1 row and 2 column. No, it is not possible. This number right here, does not equal this number right here. This does not have the same number of columns as this has rows. How about this guy? This is 5, 2, 1, 3, 4, 6. This is 2, 3, 4, 5. What do you think? Well, what is this? The dimensions of this one is 3 rows by 2 columns, and this is a 2 by 2. Yes, yes you can. This number right here equals this number right here, and the result would be a 3 by 2 matrix. So that's pretty much it for what you need to know for matrix multiplication for the ACT. Usually we'll just have things like this where you have to pick for which ones and what represents the situation we're dealing with, and you'll be able to look at some of them right off the bat and go, well, that's impossible. You can't do those multiplications. Then you're left with like 1 or 2. 1, great, you're done. That's the answer. And you're left with 2, and you can look between them and go, oh, well, which one makes sense? This is going to end up with a 1 by 1, and we want to know a number versus, or we want to know a system of equations, and this is going to give you a number. You need to know the system of equations, in which case that'd be a 2 by 2 or 3 by 3 or whatever. Okay, great. You pick that one. So dimensions everything. Just know the dimensions, know how to figure out what your resulting matrix would kind of look like. That's it. That's the vast majority of it. It's rare they actually have you ever multiply out matrices. But again, if you really want that 36, you should know how to do it. I'll provide a link in the description below. Check it out. Work some examples. We're not going to do that here. We're going to do one other thing, though. You should know how to convert systems of equations to matrices. Given a system of equations, convert it to a matrix. So let me show you. This is a very simple example. Let's say x plus y equals 3, 2x plus 3y equals 10. Okay, normally if you want to solve for x and y, great, you can do that, but it's hard to just solve for it if you have 100 equations and 100 unknowns. That's what a matrix is for, by the way. It's one of the great purposes of matrices. There's a whole discipline of math devoted to matrices. Lots of algorithms for decades have been written on them. There are computer programs that can just slice through matrices like they're nothing and solve for things. You would never do something like that crazy one by hand. These little ones like this, sure, you can do that by hand, substitution, elimination, you're good. But if you want to convert this to a matrix to have the computer figure it out for you, this is how you do it. The matrix version of this, just make sure your x's are lined up, your y's are lined up, numbers are lined up, your equal signs are lined up. Take all the coefficients. It's 1x, it's 1y, and it's a 3. It's 2 x's, 3 y's, and a 10. Then you take a line and put it where the equal signs are. That's it. This corresponds to this in matrix form. And there's a whole science behind. You can do cool things with this now, and you can solve it in matrix form as fast as you can do elimination, but you don't need to know how to do that. If you actually need to solve for these things, use substitution or elimination. Don't waste your time with matrix stuff. For 2 equations, 2 unknowns, it is not worth going to a matrix for that. When you got 10 variables and 10 unknowns, yeah, you're going to mess with a matrix. You're not going to waste your time doing substitution. That would take forever, and you'd probably get it wrong and checking your work. Oh my God. No, use a matrix for that. So let's have you do a couple of examples. All right, here's one for you. 4y plus x equals 5 2x plus 3y equals minus 6. What would that be in matrix form? All right, first thing I would do is actually have to swap these guys so I have all the x's in a row, then I have all the y's in a row, and then have the numbers in a row. So if I were to swap those, the coefficient of the x would be 1, the coefficient of y would be 4, and then the number would be 5. The next row, I have my x is 2, y is 3, and the number is minus 6. Put the bar, and I'm done. That's it. Okay? This is the matrix form of that. Let's do one more. X minus y equals 4, minus 3y minus x equals 7. What would that be in matrix form? Well, again, I'm going to stick the x's in front. This one already has an x in front, so we're good here. 1, minus 1, and 4. Those are coefficients. If I move these around, this would be minus 1, minus 3, and 7. And again, stick the bar there. That's it. They may ask you a question like this where they'll say, which of these matrices represents the system of equations given? In which case you can look at it and go, oh, it has to look like that. That's how I would do it. That's it. That's all I'm going to cover for the ACT matrices. It's probably all you need to know. That's the only kind of questions that I have seen asked when it comes to matrices. It's not that they couldn't ask anything else. I just haven't seen it, and they tend to ask the same kind of questions over and over and over. So it's good to know the kind of questions they've asked before. If you're good at taking official ACT practice exams, then you'll be fine for the ACT. There aren't many new problem types that show up. So they could ask for a different type of matrix question that I haven't covered here or in the previous video, but it's unlikely. It's a 99% chance if they're going to ask a matrix-related question, it'll be covered by this video or the previous video on adding and subtracting matrices and scalar multiplication. Anyway, hope this helps.